So before I start, we had a great talk from Dr. Frodick on the 5G pathway, the Ericsson point of view. What we have here is the vision and the challenges for the phi layer in general, but these have been narrowed down to like the channel coding challenges. So I'll just go over these three slices that we have here, and later on in the first half of the presentation, I'll talk about these in detail as to how these pertain to the channel coding setting. And then Brennan will take over and focus on the repeat accumulate family of codes and how rate compatibility can be achieved and what has been done. So the first point is, as we've all seen a few minutes back, the migration to the new mmWave spectrum, unleashing the gigahertz frequency bands available. So the challenge here is that it's a relatively unstable channel, and the takeaway is that it definitely needs rethinking of modulation and coding. The second point is the increase in capacity slated to be about 1000x over the current deployments like LTE. We have a peak throughput user experience target of 10 Gbps, and of course the latency, the end-to-end latency is 1 millisecond, which is almost a tenth of what we have now. Clearly this translates to very high throughput phi layer processing and spectrum and power efficient channel coding algorithms. Now, coming back to the subscriptions, the mobile services, the number of devices, the Internet of Things, and the whole thing really boils down to greater flexibility in code block sizes and rates. I'll define what we mean by block sizes and rates soon enough. And of course, a fast and highly adaptive Mac operation. So let's move on to the first one, which is migration to mmWave. I have tried to filter out a lot of other vision challenges that mmWave has. As we've seen, like we have to have energy efficiency, low energy consumption on devices in general, then always awake kind of instantaneous quality of service and so on. So these pertain to the channel propagation issues and how they affect us. So the first being that this is primarily a directional line of sight communication system. So although there have been encouraging results shown recently from the measurements of the 28 and 76 gigahertz urban canyon models done at NYU, in NYC, then UT Austin, Samsung Research in Korea. These figures are from those sources. So second part is where you'll see a lot of shadowing. For instance, brick mortar, building structures will see about 40 to 80 dBs of shadowing losses. Then there is something what Samsung calls as the handheld effect. When you actually hold your phone, the human body will play a role in this and contribute to further losses. So there have to be multiple antennas and beam forming and so on. There's also foliage loss, which is not too significant, but it still exists. And then the channel is a very highly time-varying channel, since it linearly scales with the carrier frequencies. There has been a study which indicates that there's about 3 kilohertz of Doppler spread over 60 gigahertz at just moderate speeds. Now this scenario we've put here is to motivate the need for retransmissions, which will be very fundamental to any small cell urban scenario. So here you can see the transmitter actually transmits a powerful signal, but when it crosses the foliage and let's say there is a moving obstacle, what Dr. Frodick mentioned to be the patchy communication link, which will be rather intermittent, So you'll see a lot of loss, and there is a high, or rather a finite outage probability relative to the contemporary systems. So what this means is that for modulation and coding, the channel code has to handle this situation, which is relatively significant and new compared to the current deployments. So that is the focus. And moving on to the encouraging results that have been shown, the solutions behind these results are things like large antenna arrays, highly adaptive beamforming, massive MIMO, and so on. And of course, robust channel coding and modulation, advanced modulation techniques. So the takeaway from the solutions part of this slide is that there is a lot of additional processing required in the newer 5G terminals, right, or devices in general, because if you imagine the processing needed for these, it's a lot. So whatever budgets we have today are going to be squeezed further. So the contemporary channel decoding algorithms, encoding algorithms that have been deployed, may not actually fit within that budget. So that's the aim of mentioning these different solutions. Now, the other challenge is high throughput and latency, and these are some pointers based on our experience and literature out there. So by throughput, we mean that from a channel coding perspective, here I'm talking about the decoding throughput specifically, which means the number of bits that you process per unit time. So a throughput of 10 gigabits per second essentially means that you're streaming 10 gigabits per second through the channel decoder. That's what the throughput means. So in any communication system, if you recall the phi layer chain of modules, the channel decoder algorithm is one of the most computationally intensive processing modules in the phi layer, especially if you have a soft in, soft out kind of an algorithm. You have the convolutionals for like the BCJR, Viterbi, or you have these factor graph based decoding and so on. They're all pretty expensive. Now when you talk about several gigabits for 5G, and here is to just give like a ballpark figure of what people are looking at, what the community is targeting is, for instance, Samsung announced in ICC 2013 that the first rollout is going to be 5 gigabits per second for the mobile handheld terminals by 2020, which is, if you compare it with 4G, it was 75. And there are a lot of other issues like how the technology will scale and what the promises are, for instance, the efficiency of power amplifiers and so on, which I have not addressed here because that would be too big a topic to talk for this focus. So moving on to latency. The latency is defined again similar to the throughput. These are highly interrelated metrics. The latency is the processing time between the first input. You input your, let's say you have a block of 100 bits. You put the first bit and the time you get the first output bit or a first decoding decision is what is defined as the latency from the channel decoding perspective. Now, the end-to-end latency, as we already saw in the earlier talks also, is very ambitious. It's less than a milliseconds for the real instantaneous like quality of service, which is almost a tenth of what 4G has. For instance, if you see the decoding latency budget, I should have been specific. This is the decoding latency budget for the 802.11n. So, for instance, if you choose the Ldbc decoding option for 802.11n or 802.16e, based on the block sizes, you basically have less than 6 microseconds to get an output. Now, the two major contributors to latency in 5G, what we think are going to play a major role. The first one is hybrid ARQ. Brennan will shortly discuss what HRQ is, but it's basically a combination of channel coding and ARQ. So, because of its inherent feedback, HRQ will add to the latency. And we are looking at certain modern codes, probabilistic codes, which I believe the whole channel coding, error control coding community focuses on these days. So these codes tend to work better for large block lengths, moderate block lengths, which clearly directly impacts the latency. Now, another important point is that the encoding is no more isolated. The encoding will need rethinking because a lot of proposals from different research groups actually talk about a symmetric uplink downlink, which means that especially for the UEs, the handheld devices, encoding becomes a major contributor to the complexity. And the final topic, which is really the motivation for today's talk, is the rate flexibility. Now here we are talking about the code rate, which is for any given code, algebraic, probabilistic, the measure of redundancy, which is basically the number of parity bits that you have per information bits. So the more the redundancy, you have a better performance, but then you pay the price in complexity in processing. Now here are some code rates. Just to give a what we are working with. For instance, 3GPP has 5 rates for the turbo decoder, which is for the turbo code, which are listed. Then we have the 802.11, 802.16 rates for the Ldbc scheme, which is optional. The digital video broadcast has 11 rates with fairly large sizes for S2, for example. Now for 5G mmWave, we've seen the applications are going to range from sensors which transmit a few bits to videos and whatnot. So heterogeneity plays a clear role. Although it's very clear that one code is not going to satisfy all these requirements. So that is why the motivation is that even if one code doesn't satisfy all these requirements, if you actually implement or generate an IP core on, let's say, some hardware, it's really not feasible to support different encoding, decoding algorithms on the same chip, used at different times on the same hardware. So the code inherently has to take on that onus of providing rate compatibility so that the hardware complexity reduces a lot. And based on our experience, this is extremely, extremely important. Of course, the efficiency of HRQ, as Brennan will soon discuss, is another factor. So I'll hand it over to Brennan now for the rest of the talk. Thank you.
Thank you. So as Swapnil mentioned, rate-compatible codes are one of our main focuses. And the reason that this is the case is because we're trying to use them in something called a Type 2 hybrid ARQ implementation. What hybrid ARQ does is it uses this combination of error correction and error detection, where we have a family of codes of multiple different rates, which all share this property where the higher rate codes, the parity bits of those codes, will actually embed into the parity bits of the lower rate codes. What this means is that if we send a transmission and that transmission fails, we can use the lower rate code to now transmit that instead and use a stronger decoding code to get hopefully a better performance on the channel. So this property of rate compatibility is best illustrated with this example. We have 4 codes chosen: rate 1, 2/3, 1/2, and 2/5. And in our initial transmission, we may send just the rate 1 code, which is just the information bits. If that does fail, then we can transmit using, on our first retransmission, the rate 2/3 code. But you've noticed that we've already sent over our information bits through the channel, so we don't need to be transmitting them again. We just need to send that red set, the parity bits, over there. This principle of incremental redundancy means that every retransmission we make means that we only have to transmit the bits which have not already been sent over the channel. And this is designed to give us a lot more throughput overall. So there are a few goals that we're looking for in rate compatibility. The first of these is a fine amount of rate adaptation, the ability to support a very large set of codes of a lot of different rates. Performance granularity, the idea that we can have a lot of different levels of performance changing the rate very, very finely. The ideal relationship between these two is that there's some sort of linear relationship. The amount of parity bits added gives a predictable amount of performance gained, and there's no big jumps, so we don't add a small amount or remove a small amount of parity and then get a huge drastic increase or decrease in performance. Additionally, we'd like to have a bunch of simple extending and puncturing algorithms to create these rate-compatible codes. This is, has mostly to do with the implementation questions. So the codes that we've been studying and looking at mostly belong to a few different classes. So some preliminaries, there's the low-density parity check code, which has two representations. One is this Tanner graph on the left, which you can see has a bunch of different variables, a bunch of different checks, and then some sort of interconnections between them. And then the adjacency or parity check matrix, which effectively describes the same thing in a slightly more compact setting. The encoding and decoding of these codes is facilitated by the property that all the variables connected to a given check node have to sum to 0. Something that is used similarly are something called quasi-cyclic Ldbc codes. These are a little bit technical to explain, but the idea is that they are described by a very large matrix that contains a bunch of different circulant shift matrices as submatrices. You can see that a -1 here will mean that we put a 0 in there, and then if it's a non-1 number, then that means that we shift an identity matrix by a certain amount to create a circulant parity or a permutation matrix. Lastly, the code that we're interested in is called an irregular repeat accumulate code. This is basically just an Ldbc code that has this additional zigzagging parity structure. And that allows us to partition our information and our parity check bits into two distinct sets on the left and right, as you can see. There are additional constructions of these quasi-cyclic IRA codes, or also known as structured IRA codes, generalized IRA codes, and then you can combine the two to create quasi-cyclic generalized IRA codes, which is actually something that we're going to be looking at in the future. So the reason that we are interested in these quasi-cyclic Ldbc as well as these IRA codes has a lot to do with the implementation of them. For quasi-cyclic Ldbc, we're going to have to do it in hardware. There's no feasible way to do it quickly in software. So we need to be able to avoid a lot of routing congestion when we're implementing these codes, and we're also going to be very concerned about parallel processing of these codes. Quasi-cyclic Ldbc facilitates both of these and also allows for a lot more easy rate adaptation. IRA codes are mostly used in standards because they are linear time to encode, as opposed to as opposed to generalized Ldbc codes, which do quadratic time. They also don't require a generator matrix when facilitating these encoding algorithms. You can just use shift registers. And the rate adaptation of these codes is a lot more intuitive than with more general Ldbc codes. So we see these codes, these IRA-inspired QC Ldbc codes right now. You can see them in the 802.11n Wi-Fi and 802.16e WiMAX standards. And the problem with these current standards is that they don't actually have rate compatibility embedded into them. So our focus has been how can we achieve rate compatibility using these codes. Some extra concerns, we want to make sure that the puncturing or extending algorithms that we choose will preserve the structure of the code. So an IRA code, after we extend, will stay an IRA code. SIRA will stay SIRA, etc. And for our purposes, just for simplicity, we're going to focus on just the extending portion. So we get these questions of how are we going to introduce these new parity bits? How will these relate to the information bits that we're sending? And how do these relate to each other? The method, which I'm not going to get too detailed into, that we've adopted really, is called row splitting. Here we take our Tanner graph, we look at every single check node and the information bits that connect to it, and we partition it into two distinct sets. Here, the red and the blue set. We introduce a new check node and take those two partitions and put them onto the different check nodes. And what we end up doing is we just extend the parity structure naturally. This will create a rate-compatible set of codes, and when you do this for a very large number of different parity nodes, check nodes, you end up creating much larger codes that preserve this rate compatibility structure and can often offer us very good performance. So there are a couple different results that we have. These are, in the red we have a structured IRA code that was constructed using this row splitting, and then in the black there's a generalized IRA code which was also created using row splitting. It's important to ignore the absolute results, the absolute bit error rate performance of these codes, because actually they're not very good for these particular codes. But it's important to look at the relative performance with each other. So the rate 2/3 codes we can see have a pretty big gap in their performance, indicating that there's something good happened. We have a good amount of gain that we get when moving from a lower rate code to a higher rate code. And the same thing happens from a rate 2/3 code to a rate 1/2 code. So we've been focusing a lot on this row splitting technique and doing this for a variety of different codes, including generalized IRA codes. Our current applications are focused on the development of good row splitting algorithms because these are not trivial, although many effectively random algorithms do perform very well. We've been looking at applying these row splitting algorithms to broader classes of codes, in particular the generalized IRA code, as well as the structured IRA code. And then finally, we're interested in having a lot of granularity in the row splitting algorithms. So this row splitting technique that we use is very good in that we don't have to split every single parity bit at once. So it does offer a lot of granularity, but we need to be observing that more carefully to see what exactly happens. So thank you very much. Swapnil and I will be available for any questions.